Another application of Ampere's law can be obtained in a similar device called the toroidal solenoid. And so let's take a look at that. A toroidal solenoid, you can think of this as a regular solenoid, a cylinder, that you curve around and attach the two ends. And so it really is like a donut. Okay? It's got a hole in it, and it's got a cylindrical cross-section. And then you wrap a current-carrying wire around it. The way they're wrapped, if you look at these, look at it from a side view, cutaway view. Here's the donut portion. This is the hole section here. And if you look at any side of it, the currents on the interior is coming up, and on the exterior is going down. And interior going up over here, exterior coming down away from it. And if I view it from the top, well, here's the donut portion. Here's the hole in the center. I've got the hole in the center as radius R1, and the outside of the torus, it's really a torus, is R2 from the center. And on the interior, all of these wires are coming out at us, currents coming out, and on the exterior, they're all going away from us if we're on top of this looking down. Okay? And again, we can apply Ampere's law to it. If I use an R like on C1, I've got a total distance from the center C1 of R all the way around. I'll go around in that fashion. Well, it's pretty obvious that for every wire coming up, I've got one going down. And so every one of these going into the page, there's one in here that's coming out of it. And so the total number, I've got as much current going one direction as the other. So the total current cutting the area enclosed by this curve C1 is 0. And with that, the magnetic field vanishes again I have a finite DL, and the directions are such. So it's the same story. And that's what you would expect if you think of this torus as made of a cylindrical solenoid that you curve around and attach the two ends of it. So everything is, the magnetic field vanishes outside a solenoid, and if you just curve it around, it still vanishes. So B vanishes because the current enclosed vanishes. Inside, it's a little bit different, and they usually present it in a slightly different way. So here is the interior. I have a exterior. On the interior, they're coming out at you the way I'm looking down. Exterior going away from you. I just did two of them, but it's all around on the interior and exterior. And then curve C. I'll take in the direction of the magnetic field. So you expect the magnetic field to be going down the axis of a solenoid. The cylindrical, if you curve it around, it's just circulating about it in this fashion up here. So magnetic field is now going in this direction, but only in between R1 and R2. And if I choose my curve between R1 and R2, then I have this picture looking down. B.dl is mu total cutting. And now, if you look at this, only the ones coming up here cut through, but it's all of them. And so the total current, I've got N turns, capital N turns, and they're all coming up at me, and so N times I is the total amount of current. My dash curve here is C2. And it's in the same direction as the magnetic field, so B.dl just becomes B of R dl. I'm at a constant radius, and so a function of a constant is a constant, and I pull that out. And you get the magnetic field in the donut portion, in the part of the donut that you eat, is just given by this expression, so long as R is between the inner radius and the outer radius of the thickness of that torus. Inside, it's much the same as before. Inside here, my field is all circulating about in here. There's no currents that pass through this curve C, so there's 0, and that leads to B on the interior. Again, it's the hole in the donut is going to be outside the solenoid that's curved around, and so the field vanishes there. So altogether, kind of an interesting geometry, but you get this expression. If R is less than R1, that's inside the hole, there's no field. And R greater than R2, there's no field. Only time you get a field is in the interior from when R is between R1 and R2. It falls off as 1 over R. And it falls off, one can make it pretty strong if you just had lots and lots of turns. So one advantage of this configuration is there's no field outside, and it's self-contained. It's not real long. It's just a continuous strand, continuous donut shape. And you can make the field on the interior very, very strong by just having lots and lots of turns all carrying the same current. Inside, it goes off, it's 0 outside, so I didn't even draw those here. The only place there's any field is between R1 and R2. Falls off really fairly gradually. On the inside, it's a little higher because R1 is smaller, and I'm dividing by a smaller number. Outside, it's a little bit lower, a little bit weaker on the outside edge. Usually, people use what's sometimes called a thin torus approximation. So here I've got a thin torus where R1 and R2 are very close to being the same number. And for those, what they typically do is take the central value, which would really be the average of R1 and R2. That would be the one going right down the center of that. And then just use that for the value of the magnetic field in the interior. If you look at that, that's this. Mu naught n times I, 2 pi rc, but 2 pi rc is essentially the circumference of this. And so again, the number of turns divided by the length, in this case the circumference, is the number of turns per length, again in this torus arrangement, and so you get back to a form that looks very similar to the cylindrical solenoid. Oftentimes you will see these donut-shaped wire coils in the laboratory. So they're little small coils of wire. You see both. You'll see little cylindrical coils, and they are solenoids. They will sometimes call them inductors. So don't be surprised if when people say an inductor, they're probably thinking about either this toroidal shaped solenoid or a cylindrical shaped solenoid. And the formulas are very similar. In fact, they're identical if you interpret this this length to be the circumference of the central portion. And the formulas are very simple. It's just to use. They're very, very good approximations, often used for the magnetic fields inside cylindrical solenoids and inside the toroidal solenoids.